All right, so what we have left for this handout is the extension from last time. That I think you kind of like it better than electric field. All right, this is an electric potential. And we saw from last time that this one is not a vector sort of like manipulations anymore. So your math seems to be a little bit less complicated, right? Because you only add numbers together. You don't have to worry about directions anymore. So that's easy. However, what we did last time was like we trying to stick with two things. All right, so let me give you a quick recap. So the first thing is one way that you can calculate the potential difference, right? Just a quick reminder, most of the time when you talk about potential, you are calculating potential difference. Okay, you don't do a single location potential. Usually it must be referenced to something all the time. So that means every time you do a change of the potential, which is we name it potential difference, you can do it one way if you know the electric field. Okay, so that means if electric field is given to you, all you need to do is just take the displacement and do the dot product between them and do the integration. And the key thing that we explained like 25 minutes trying to give you understanding of this whole business is where the negative sign is from. Okay. In conclusion, what we can say is every time you go against the field, you are going up higher in potential. That's the whole point of the negative sign there. Okay, cool. All right. So, and once again, you can make a very, very good comparison with the gravitational field. Okay, when you go up against the gravity, you're going up higher in potential. Same thing. All right, same idea. All right. The second way that you can calculate the potential difference is when you are given, once again, point charges, Qs, right? When you have like a lot of Qs around and you want to calculate potential at a single point, then you can use this sort of like a very, very mini equation over here, KQ over R. And once again, every time that you see this equation, it means you take infinity to be your reference point. So that's why we don't need the delta anymore. Okay, it's always a delta with respect to 0 at infinity. Okay, so that's why every time you see a point charges or a bunch of point charges, and then you would like to calculate the potential at a point, all you need to do is just collect this KQ over R, just sum them all. Okay, so that's what we did last time. And it's kind of fun for a while, I guess. All right, so all you need to do is just collect all KQ over R, on and on. We do a bunch of geometry of the distribution. Everything is good. Here's today's question. What if, once again, just like what we did in the electric field, if your charge or your sort of a distribution of charge comes out to be a continuous manner. So it means they distributed continuously throughout some, maybe matters, or it could be some spatial, or maybe some part of the stuff in space. What will be the potential at a point? So this is it. Now you have like a cloud of electrons, you have like maybe a cloud of protons, or you have a distribution of charge around some conductors, on and on. What is your electric potential at point P? Okay, once again, the calculus will come in. Here we go, guys. So this is a calculus day. Okay, so what we're going to do is we're going to extend the formula that we did before and re-express it in terms of the integration. And now it's your job to do your slicing of the charge yourself, just like what we did in electric fields. Sounds cool? All right. However, just to give you some familiarity, so you may notice one thing, wait. What is this bunch over here? What is this? It looks complicated than before. So the answer is, don't worry, we'll review this later. But for now, this whole thing is our K. Same thing. All right. So that means K that we have before can be written in another form that based on another constant, the epsilon naught over here. All right. But we'll explain what is the connection between the two. All right. But this one just so to give you some familiarity. All right. So this is the full extension of what we did last time. We started from V equal to KQ over R. When you have more than one, you just do the summation. And if you have a continuous charge distribution, You just need to do the integration. That's it. All right. So it's a natural extension from what you usually do. And you bring in the calculus to do something that is continuous. Sort of like a characteristic in there. All right. Very cool. Are you ready for the fun? All right. Okay. Very cool. Here we go, guys. Let's start from this annoying one that we did last time. Remember, we tried to calculate the electric field at point P that came from, bunch of charge on the rings. And then we have to do the electric field. And then we have to break it into two components. And we argued that the perpendicular components cancel each other out, on and on, right? We do a bunch of stuff. Here we go. Same system. But now we are interested in potential instead. That's it. That's what we're trying to do. All right, guys, give it a shot and see how it goes. All right, for those of you that just came in, all right, so there was a quick announcement. On Wednesday, we are going to have a Q&A. All right, so as we said, and because we're going to do the same thing on the second section, so section 2 as well. So you have another slot on Thursday at 2 to 4, just right before the exam. Okay, that will be, so it's like you have 2 time slots if you want to join in and have any questions. Okay, and during the Q&A, if there is any question that I can give you solutions, then I will just try to write it down like on screen and capture it, put it in a PDF form, and I'll just submit onto our Google Classroom. All right, so you guys can check the solution. So if you miss one or the 2, then the second one probably you don't have enough time anymore. But anyway, so if you missed that class, I mean, if you Wednesday you don't want to join, you can catch up on Google Classroom. All right, so I will put that solution on, or the video actually as well. So I will do the video and then just upload it right after the session. Okay, so I'll try to give you a good preparation for that. All right, and the last thing that I say was I'll try to make this exam look similar to the exercises as much as I can. Try to, not trying to deviate too much from the exercises. Okay, all right, guys, so how are we going to do this? All right, same thing, right? So we're going to have to slice the charges ourselves. Do it. So we're just going to slide sharp over here, and that will contain a little bit of charge dq right there. Okay, and now because we don't have to worry about any directions, all you care about is what is the distance from this dq to the location of your calculation, which is at point P. Okay, so what I can say over here is just say, okay, John, potential is just K, the charge generating that potential divided by the distance. No need to square or anything, right? That's it. All right. However, we said every time that you're generating the potential from a super tiny charge dq, you're going to generate a super tiny potential as well. So let's call this dv for now. Cool. All right, and then you're going to start to do this at other locations like dq, right? Every single point on this ring will get sliced and calculates throughout the rings. However, if you notice, wherever you are, this expression works no matter where you are. Cool. With me? All right, so that means no matter where your dq's are on the ring, you can still use this expression dv equal to k dq over square root x squared plus a squared all the time. So that means all you need to do is sum them up. With me, guys? Okay, you just add all of the dv that generated from all the dq on the ring. So all you need to do is just do the pure summation of this whole thing throughout the ring. Once you're done with that, that's your net potential at point P. See, it's kind of easier because what we did last time was the field and you had to take care of the directions. But now, because it's just number, you don't have to do anything, just add them together. Okay, so now complete your integration for me, please? Or is that yours or mine? So this is my integration or yours? Okay. Alrighty. When you look at this, Negro is once again, Ajahn, wait a second. The K is constant. I can pull it out. That square root x squared plus a squared is also constant, right? Because there's no variables over here. A is constant, it's just a radius of the ring. X is just a distance from the center of the ring, it's fixed, they're all fixed. So actually that square root come out as well. So all you need left to integrate is just the charge on the ring. And what is that? That's just the total charge Q over there. You guys with me? All right, so that's it. Too easy. I'm done. That's it. Not bad. Wow. No, I'm not quite care like that. Whatever. All right. Yes.
After the integration, we get Q.
The lowercase, you can think of it as a variable, but we use it to represent charge that you slice from the ring. So it's sort of like the amount of charge that contains within that slice. So you can think of it like it's the quantity, the amount of charge. So it's still in the units of course. It's very small, approaching zero. Yes. So once you sum all those integral, you get back the total on that ring. Okay. All right. Cool. All right. So that it is done very nicely, and it's easy. Try again, guys. Next. What about this? I think something is missing. Where is the rod? Uh-oh, maybe I accidentally deleted that one. Oh no. Uh-oh. It's supposed to have like a straight line. I mean, a straight rod before this one. Oh, okay. All right. I'll do it myself. Sorry, guys. We're supposed to mirror image everything that we did before. Okay, so let me write this one down. Something is missing here. Okay, so another one that we did in class was this. So you have, remember this? Okay. And you have a rod. There you go. Let me write it like that. Okay, so you have a rod. Okay, that's to look so nice. Let me do it correctly here. So you have a rod of length L, and you place it on an x-axis. Okay, at a distance A away from this. So this is at A. The length of the rod is L, so this is A plus L. Remember this problem here? You would like to calculate the electric field at the origin. Okay, and we are given that the charge per unit length of this rod is lambda. Okay, so this is a missing slide over there. I don't know where to go. All right, so find what potential at point P. There you go. All right, guys, so I think this is important. I don't know where did the slide go. So it's exactly the same setting that we did with the electric field. All right, but now we would like to get the potential instead. All right, same thing. Did I get all everything? Yeah, I think it's good. The distance is A, the length is L, the charge per unit length is lambda. Okay, very good. All right, guys, try this. It shouldn't look too bad now. We did like the harder one with the electric fields already. So this one is supposed to be easier, relatively easier. All right, for those of you that want to get things started, you probably do the same thing here. You slice this into a tiny piece, DQ, chop, chop. Yeah. Okay, inside this DQ, we'll have the amount of charge. I mean, it will take up some space, dx, chop, chop, right there. Okay, and if I just pull this DQ out and do the analysis, like sort of like isolate them. So this is the amount of charge. The distance from the DQ to the point P that you want to calculate will generate a tiny bit of potential dV. With me, guys? Okay, and you will be able to write right away, like, okay, that mini potential there will be K times that mini Q divided by, because you already laid everything on an x-axis, the distance that you have right here is automatically X. So you put X there. Right? So that's where you can get your potential from dq at the location of X. Then you try to do this at the point you start slicing from the left end of the rod, dq, 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 all the way to the right end of the rod. Okay, but no matter where you are on the rod, the same expressions apply. Right? Because you can always calculate the potential dV directly from K dq over X, no matter where your X is going to be. There you go. So that means all you have to do is to add those dV together. With me? From the left end of the rod to the right end of the rod. And once you've done this, that will be your net potential at point P. Cool. Not bad, not bad. All right, so if you're okay with this, finish this integral for me, please. มาพอได้ไหมพอได้ไหม You try to do the same thing as you did before, except this time is easier. There's no directions, right? That you don't have to worry like electric fields pointing you your left on and on. That's none. It's just a number. So first, whatever constant, you pull it out. But of course, X cannot be pulled out, so it has to stay there. So what we did before was just like, okay, John, we have a problem a little bit because we have a dq as our variable. But the integrating function is under X variable. So somehow you have to convert dq into something of dx. Okay, and what we did last time was, well, John, this is easy to do because this equal to, right, remember this? There you go. If you try to connect between the dq and the dx, that factor is just the lambda, because the lambda is charge per length. Okay, so if you know that the length that you are in consideration is dx, you want to know how much charge is inside that dx, then all you need to do is just multiply by the lambda. Okay, the lambda is just a charge density. It's per length. So the length is dx, multiply the lambda with the dx, you get back the amount of charge inside that dx interval. So that's good. So that means I can turn this integral into integral of 1 over x lambda dx. And now because everything is written under x, now I can put the lower limit to be a, the upper limit now is going to be a plus l. Isn't that cool? All right. And because for this particular problems, the lambda is a constant, because right now it seems like according to the problems, the charge is uniformly distributed. So right now the lambda is a constant. So that means I can pull the lambda out as well. So you're only left with this 1 over x dx integral, and everyone still remember how to do this. It's a natural log, so it's a ln x, and then now you put the limits of the integration there, and that's it. Your final answer will be k lambda log, then you can put a plus l over a, and that's it. You are done. Okay,ไหมครับ? Not too bad. Okay, very good, very good. So it looks pretty nice. All right, so I would say this is going to be the most complicated portion of the course, because you have to integrate, you know, a little bit of calculus into your calculations. But I would say this is still one step easier than the electric field integral. Okay, because it's just pure numbers summation. Okay, don't need to worry about, you know, components, you know, separate this in x and y component. No, you don't have to. Just add them. All right, so far so good. If this is good, keep going. Today is like we practice for the final exam or something. All right, guys, next. So if you guys have seen those two problems, you should be able to execute this one on your own. And this will definitely lead you to the exam question. Oh, wow. Okay, kind of like commit. Like, okay, I am going to give you the exam questions. All right. That's related to this. Already. Okay. You have a plastic rod. Now you bend it into a form of an arc, but we have seen this already from electric field calculation, right? And now the amount of charge on this rod is given 25 picocoulomb, and you guys still remember the pico is 10 to the negative 12. It's been bent into a circular arc of radius given, okay? The angle in the middle is supposed to be phi, sorry guys, it's not theta, there you go. All right, the phi is 120 degrees, just like previous problems. Let's set v equal to 0 at infinity. We always like this one because whenever you see this, that is a confirmation that you're supposed to use v equal to kq over r. Right? And you're going to see this all the time. It's like, okay, because that's the only expression for v that we are going to use in the course anyway. What is the electric potential at P, guys? At the center of the rod. All right, we did this back in the electric field problems, quite complicated because you have to break this into two components, on and on. Vertical components cancel, you left with just the x components, you sum those, get the final electric field. But now we don't have that problem. We only have to sum the potential. This can be done in 1 minute, this problem, seriously. All right.
We skip it. We see it in 1 minute. We skip it.
If you want to skip, it takes less than that. All right. So this one should be able to, you know, complete the calculation within 1 minute or less. It will be less if you have seen it once. So you do it second time, it will be less. And if you see it third time, it will be like 15 seconds. And if you see it fourth time, maybe it's just like 2 seconds, and then you can answer right away. I think so. Actually, well, it's more like when you see, and then you know the answer, it's that fast. All right, but anyway, initially we have to show you how it's done first. All right, guys, slowly think about this first. How are you going to proceed? This is not bad. All right, so you follow the same method that you did before. So I'm going to slice this into a tiny piece, right? This is a dq. So the distance from the dq to the point P is radius r, so no problem. That would generate a tiny potential dV equal to k dq over capital R. You guys with me here? All right. And the complications that we had with the electric field disappear now, because what you're going to do is you slide dq from the top to the bottom, or from the bottom to the top, doesn't matter. This potential, you still have the same value, k dq over r, right? Okay, so all you need to do just once again, sum these together. You will get the net potential at point P. Yes. Okay. However, you look at it, but wait a second. K is constant. The radius R is constant. There's nothing to integrate here. K is out, R is out. You only have to sum all the dq on this rod, and it's just capital Q. And that's it. I'm done. So we actually can use the original trick that we did in like maybe the first problems that we faced last lecture, because all of those charges are at the same distance from point P.
Oh, we cancel.
No, we pull a common factor out, and all you need to do is just sum the amount of charge. Remember that? Okay, if not, let me flash back a little bit. Remember this one? We said, okay, John, I would like to calculate the potential at the origin, but that charge, they are located at the same distance from point P. Right? So what you need to do is just sum all the charges and then multiply by the K over distance, right? It's like you have K over distance to be your common factor, and then you pull that out and you sum just the amount of charge. But the only thing that's different here is just the charge is just continuous. But I mean, logically, it's no different, because all you need to do is all the charges are at the distance or away from point P. So all you need to do is just how much is the charge? It's the capital Q. That's it. K capital Q over R. You're done. Cool. All right. So that's my point. I'm saying, like, yeah, you don't really need a lot of calculus here. Yes.
Oh, okay, so that's
Yes. No, the charge cannot cancel each other if they are not at the same location. Right? Because you just arrange the charge into a ring. So all those charges distribute that way. There's no cancellation or anything. But you are interested in the potential away from those charges. That could be a cancellation there. That is possible. I think what you're asking here is this. If you have the whole full ring, right? The center will have zero field, but non-zero potential. Does that make sense? Because the field is the vector, right? So when you have a full ring, the vector will completely cancel around the ring. But that's perfect. It's zero field. But the potential itself just adding up. So you're not going to get zero potential there, but zero field. That sounds counterintuitive, but it's no big deal, because potential is just the height. The field is the force, right? So it's possible for you to be at a very, very high altitude with no force, because you're standing at the top of the mountain, right? When I'm standing at the top of the mountain, I don't have any force, right? But my potential is high with me. So that's what it means by zero field, but non-zero potential. Because potential is just my elevation. I can sit, I can stand, I can go everywhere I go without any force acting on me. Yes. Cool. All right. But that's a good question. Yes, that's actually point into the direction of the comparison between the field and the potential. All right. So everyone seems to like go in the same direction that, hey, zero field means zero potential, or zero potential means zero field. No. Right. You have to look at the change, not just the value itself. So if you're just talking about the value, it's possible to have zero field, like you said, with the non-zero potential. That's possible. Possible. Okay, cool. Very good question. Yes.
So it's like potential derived from field, right?
They can go both ways. Yes. So you can calculate the field from the potential or the potential from the field. But the derivation is not one-to-one, just purely. It's not like you transform from one to the other. You look at the change, right? Like you want to have to go from the potential to the field, then you have to look at the change of the field. Or if you want to go from the field to the potential, you have to do the integral. So it has like a derivatives built into it. Yeah, yeah. All right, very good question. Yeah. All right, guys. So I hope I'm showing you sort of like, you know, a little bit of peace of mind that this calculations about the potential is not that bad. All right, guys. So this is the old questions back in the, I don't know, my old exams, or I always put this one on, but you should be able to do this in now. Guys, try this. This is, even though it's a couple weeks from now, but this is going to be question in the final exam. I'll try to stay very close to this. All right, but at first, if you look at this problem, it would look like, oh, are you serious? It's going to be like a lot of integral. No, but no, now you see, and then you have already saw what we just did, and now you see better that, okay, this is not bad. All right, so everyone try this. It's very good. All right, so in the figure, you have 3 thin plastic rods form a quarter of a circle. Yeah, so you have 3 quarter circles with a common center of curvature at the origin. The uniform charges on the rods are Q1, Q2, and Q3, all right, given the numbers and the type of charges there. What is the net electric potential at the origin due to the rods? Woo. They want to find the potential at the origin due to these 3 rods. Looks complicated at first, but from the experience that we just gained from the previous exercise, this is easy. You can get this done in 30 seconds. Maybe I'm exaggerated a little bit, but yeah, pretty close. All right, so the way that you might be able to do this in the exam problems, if you want to, you can just make the argument right away that if you look at, let's say, start from the Q1, that Q1 at the 1 centimeter away from the origin. So you can just do that. Let me call this V1 then. That's my V1. And then you keep going, you're going, and Q2 is at 2 centimeters from the origin. You can call it, it's going to give you V2. And then the last portion, there you go, it's at 4 centimeters. It's going to give you another V because they are at the same distance from the origin, V3. There you go, see? Right? And from the previous exercise, you already know how to do that from an arc. Because we already argued that whenever you have charges sitting at the same distance, all you need to do is just do the K and then over the distance, and then you collect all the amount of charge, right? So that's why I said this one can be just say it's a K Q1 over 1 centimeter. All right, I can put it in meter right now, 0.01 plus for the blue K Q2 over 0.02 plus Q3, the green K Q3 over 0.04. Believe it or not, it's done. See, that's it. There's no integral. Because we already tried and it says easy, the integration, no need. Just the sum of the charge at the same distance, and then the potential is just KQ over distance. You're done. Isn't that nice? Okay, so this kind of problems look complicated at first, but when you have already seen it once or twice, then all right, it's easier than you think. So that's it, guys. That's your net potential at the origin right there. Done. Cool. All right, very good. All right, no? Okay, all right, guys. So this is going to be the last portion of this lecture over here. So I just told you guys that came in. I think I'm just gonna finish today's lecture a little short just to complete this handout, and I think we call it done. Okay, because you will have time to prepare for the second exam. All right. So I don't think it's gonna be a good idea to push further to the next stuff, because the next stuff is actually the hardest part of the course actually. So and you guys probably not gonna have any concentration for that. All right, guys. So the last stop, I'm going to try to make the whole thing come in a complete full circle, what we have been studying about the potential. So I'm just going to circle back to the potential energy. Okay. And I would say among all the stuff, I would say this is maybe the one that I really want you to do. So I mean, with confidence, I even gonna be sort of like 100% guarantee that this problem at the end of this slide is gonna be in the exam for sure, because this is testing your understanding about the potential and potential energy. This is it. All right. So without this understanding, I mean, whatever I have been teaching is going to be useless pretty much because, all right, we explaining for 2 lectures for this. So here we go. One more time. If you want potential energy, how would you do it? Right? Because we started everything from potential energy, right? We won't introduce potential by saying that it's just the energy per unit charge, right? And then we do all the calculations about the potential V. And now I want to circle you guys back to the energy. How would you do it? All right, so look at this one. So let's say if now you have Q1 and Q2. Okay. And think about it. If the potential at point P must come from the Q1 charge, right? At the location P, because Q1 is right there. We're not calculating the potential on itself. It doesn't make sense. All right. So here comes the question. How much work is needed if I want to place the second charge Q2 at that location P? Whoa. Okay, one more time. All right. So this is pretty much the original question actually, but sort of like talk about it again. F Q1, let's forget about Q2 for now. I have the location here. Let's say how much work do I need to drag in another charge here? And you may be wondering, well, where you want to drag it from? Okay, because we start from reference point. So let me say I have Q2 from my house. I'm so far away. I want to drag it here. How much energy do I need to put Q2 right here? So this kind of question is just like, oh, God, this is for fun. No, because this is how you actually build material. So think about it. If you have like, okay, for ionic material, sodium chloride, maybe, yeah. So there is a positive sodium ion and negative chlorine ion, right? So I have to put them together. So for you to example, you need to provide energy to it. And once you have it, that structure, have some energy. And this is the start. And if you want to do like the bottom up approach, you want to build material from put atoms next together and then do like a 3D printing in atomic scale. This is what you bring the charge this, and then you bring in the third and the fourth one, build a structure, do a lattice, crystal structure, or whatever, and then you build up a bigger one. All right. So this is a try to put into your system. So, all right, so we do a simple one. I have Q1 waiting for you here. How much energy do I need to bring in the Q2? It must be easier than you think. I mean, not than I think, but I mean, it must be easy, because if it's complicated, we're probably not going to try to study it. So the answer is easy, guys. First, well, Ajahn, can you calculate the potential at point P first? You guys with me? Okay. The potential at point P, you imagine like you have like a mountain. This mountain is being generated by the Q1, right? It's a mountain of electric field, electric force, electric potential, right? So the potential at point P is just K. Okay, right now I'm trying to write it in a different form, but don't worry about it for now. But this is a K, Q1 over the separation, right, between point 1 and point 2, right? Okay, so that's it. So that is a potential at point P. Now I want to drag the Q2 charge there. How much energy do I need? But then you define the energy to be K, Q1, Q2 over separation of them before. And then you define the V by saying that it's just the energy per unit charge, right? But now we're doing backward. We start from the V, we want to go back to the U. What do? Just multiply back the charge. So that's it, guys. Let me zoom it in. This is it. Take the Q2, and then multiply by the VP that you just calculated. Bam, you're done. Too easy? Okay, one more time. One more time. All right. So I am dragging the Q2 to the location P, right? How much energy do I need? All I have to know is how high is point P. Okay, back to this. I have a mass. I have a mass so far away right now, right? Okay, far away means zero potential. Okay, because in the electric potential, zero means infinity, right? So this is my mass. This is zero height. So this is my infinite reference point. And I say about, hey, everyone, I want to bring this mass to 1 meter high. Okay, how much energy do I need to supply to this? Everyone will answer me mgh, mg1. How can I do that? I take the mass, multiply by the height, I get the energy back. With me? So that's why in the potential business over here, we already define that the energy per unit charge is the potential. So how much energy do I need? I just take the Q that I want to drag in and multiply by the height of that location P. Bam, I'm done. That is the amount of work that I need to supply to this whole system. Okay? ทุกคนดูไม่ ดูนิ่งผิดปกติ Alright, but I think it's kind of okay. It's kind of okay. Alright. Okay. Okay, one more time. Okay, so okay, I don't know if this analogy works or not. Okay, so this is my 1 kilogram. M is 1, right? This is 1. So when I say 1, mean that's the V is the potential, right? Not potential energy. So right here, this is my reference. Right here is before is mgh, right? But m is 1, so it's just a gh. Okay, so this is the potential for 1 kilogram. It's a gh. So now I say about, hey guys, how much energy do I need if I want to bring a mass m to this height, gh height, the gh level? All you need to just say that is mgh. I just put this, bring it from 0 to gh level and multiply by the mass is a mgh. Okay, so now reimagine again, if this is 0 potential, electric potential, and over here is VP, right here. This is potential at point P. And this is now my charge Q2, right? How much energy do I need to bring the Q2 from here, 0, to this VP? Q2 times VP. Charge multiplied by the potential difference. Cool? All right, so that's what it is. And don't forget, this every time always attached with minus V at infinity, right? All the time. Love it. So V at P is actually means V at P relative to 0. How much energy do I need to bring the charge Q2 from infinity to point P? It's just Q2 times VP. I'm done. All right, all right. เริ่มสนุกแล้วไหม No. ไม่ค่อยสนุกอะไร Okay, try again. Here we go. Almost done. So is it okay, guys, if I just power through, just get it done, and then you guys can just go? All right, we don't have to break in between, so save you 10 minutes. Yeah, sounds cool. All right, guys, try again. So now I have a more complicated system over here. Now I have 5 microcoulomb on the left, negative 2 microcoulomb on the right, and I want to bring in the third charge, 4 microcoulomb from so far away, infinity, to point P. How much energy do I need? ทุกคนเริ่มเก็ตยังทำไงบอกอาจารย์ This is easy. Because all I care about is what is the potential at P, right? Because all I need to find out is just how high is point P. And if I know how high is that per unit charge, all I need to do at the end is just multiply by 4 microcoulomb, and I'm done. Okay, let me highlight this in red. there. I want to drag this microcoulomb charge from infinity and put it in there. Okay, isn't that cool? Yes? No, I'm not done. Are you done? Come again? About the exam? Okay. Of course, yes. But you guys, are you guys done? Okay. Around here. I know. Wait a second, man. Lecturing here is obvious. I'm not done. No. Yes.
Why is K is not 1 over 4?
What K? Okay. Oh, okay. I will explain that next week. Yeah. But for now, it just say there is another form of the K. But they are the same thing. But actually, K has the behind the scene that is related to another constant. Yeah. It's still constant. Yes, yes. So I just give you some familiarity with this. Like, hey, I can always write K or this 1 over 4 pi epsilon naught. All right, they are the same thing. Okay, all right. So that's it, guys. So the whole point is all you need to do is just calculate the potential at point P. And once you're done with that, you multiply by that 4 microcoulomb. Bam, you get the energy that required. Yeah, yeah. That's pretty good. All right, so about that, we already practiced this. The potential at point P came from this 5 microcoulomb followed by this negative 2 microcoulomb. Okay, so all you need to do just K. Okay, right now, just K. This is K. All right, Q. Let me do the blue. 5 microcoulomb divided by 4 meter. Followed by the green. Don't forget the negative side, guys. That's important all the time. Every time you calculate the potential, that's important. Okay. And as you can see at the end, the net is positive. So that means location P is higher than 0. So if you want to drag the charge from infinity to that point, how much energy you need? Just take that VP that you just calculated, multiply by 4 microcoulomb, and be done. That's it. Okay. And the reason that this one is positive automatically give you positive work done means you have to drag this uphill because the potential at P is higher than 0. Make sense? So it's like you drag that 4 microcoulomb uphill, put it up there. So it's can give you a negative number. So that means the potential at that point is lower than 0. So the work is negative because you have to sort of like, hold back a little bit. So it's you're doing a negative work because it's about to roll downhill. So you have to do a negative work done. Does that make sense? All right. So if it's positive, you're trying to do it uphill. So you have to supply the work. But if it's going to roll downhill, you're going to have some work gain back from the system because you have to hold it back a little bit. Things work inside. It's kind of like already set and it's working in itself very nicely there. Okay. All right, guys. So that's it. Last slide of the day, guys. And we can call it done. And I would say, guys, this is either this or I will have another kind of exercise for you. And that's it. For this particular point of the lecture, I have to have this on the exam. Because other than this, I mean, it doesn't have to be too complicated than this. And this is enough for testing your understanding of the whole business that we are doing right here. All right, guys. So let's take a look. And I hope everything will come into full circle right here. All right, let's spend time with this. Maybe it takes like 5-10 minutes, but we are going to be done with this. But this is the most important point in the whole business of potential here. In a rectangle of the figure, all right, the size having the length given already 5 centimeter, 15 centimeter, no problem. Q1 is given, Q2 is given. Let's take potential to be 0 at infinity all the time. So no big deal, but no problem. This means we are going to use this KQ over R. Now, question number 1. What is the electric potential at the corner A and B? This is easy. Okay, the corner A and corner B is easily calculated potential. So let's attack that one first. All right, so part A, the potential at A is going to be, you're going to have 2 contributions from that. It's going to be from Q1 and it's going to be from Q2. Okay, all right, so that is no problem. Well, okay, John, it's going to be K. Q1 is negative. So let's say -5 is a millicoulomb, 10 to the -3 coulomb, over, now the distance over here is 15 centimeters. So let me put it 0.15 meter there. So that's what it is. That's the VA from the first contribution from Q1 plus K, and Q2 is positive. So it's going to be positive 2 millicoulomb there, divided by, now the separation is 0.05. Cool. That is a potential at A. All right. So we'll do the same thing for the B corner. At corner B, you will have contribution from Q1 and Q2 exactly the same, but I mean, geometry is different. The value is different. So you're going to get some different number. V at B is going to be K. Q1, still the same, -5 millicoulomb, but now your distance is 0.05 instead. So the number will be different, of course. There you go. Alrighty. All right. I really want you to calculate this for now. All right. So what I really want to do is I want to get a number out of this a little bit. So let me do this. So V at A is going to be, I can pull K out. So what you're seeing over here is, okay, let me do 3, 6. So it's going to be 10 to the -3 over 0.15 coulomb. Okay, that's a number right there. Okay, and I will do the B. So let me just do the scratch paper right now. It's just nothing more to it right now. It's a -15. So it's a -13 over 0.15 times 10 to the -3. There you go. There. All right. My whole point that I want to do the numerical calculation for you is this. At A is still positive. Okay. At B is negative, which is fine. So it means at the corner B is deeper, lower than, think of it like deeper than just our surface right here. At A is up the hill, up the mountain. Cool. Now, the important question is part C, the third question. How much work is required to move the third charge from B to A along the diagonal of the rectangle? That's it. That's the main question. I want to drag the third charge from B to A diagonally. How much energy is needed? B to A, that's important because going from B to A and A to B is going to give you an opposite sign, right? So we really want from B to A. All right, here we go, guys. So just to give you a sense, all right, and before I do the final calculation over here, this is it. You have the Q1 of -5, Q2 of +2. So this is what's happening. All right, I can do this. Q2 is -5. Okay, is that right? So let me do this. Q1 is 5. Q2 is 2. All right, so let me put 5 there. 3, 4, 5, and Q1 is Am I doing it positive and negative correctly? Q2 is positive. Okay, very good. Here we go. So this is what happened, and I put it in a rectangular form. Approximately, this is going to be pretty close. All right, guys. So this is it. The upper left corner is -5, and the lower right corner is +2. Now I'm going to turn on the voltage. Bam. Here we go. All right. And as you can see, the red is positive, the blue is negative. Okay. And what I can do, this is as promised, but even though we don't do much of it, but this is what we can do. I can pretty much draw the equipotential surface, the layer of the same voltage. And hopefully this will give you a rough idea of what we are doing right now. There you go. All right, and let me show the value. Bam, right there. I don't know, can you see the numbers? What it is? See this? This is 1.9 volt, 4.5 volt, 8 volt. So this means the closer you get to this, you're going to get at the higher value. So if you look at the green layout contour over here, this is the top of the mountain. With me? All right. And when you go this lower, so now numbers go more to 0 and they go negative, -6, -10, -15, -20. So this is deep down here, right? So this is going to be diving down, right? Super deep. Okay. So now here comes the question. Question over here is, you are standing at the opposite corner over here. I have the third charge sitting here. I want to drag this charge cross this to the opposite corner. How much energy do I need? Really? So it's just like you are trying to drive a car, all right, within the valley of the mountains or the stuff, right? You want to drive the car this side of this whole thing. How much energy requires? You mess from here to there. Got a point here, okay? All right. So I hope you see how can you visualize the potential in terms of, like, you know, the valley and the mountains or the stuff. And that green line right there is an altitude map telling you the height or the elevation of your whatever geography that you're trying to navigate through. But our calculation is much easier than that because we already understand how it goes. What you what you care so much about this calculation is just all you need to know is just the potential. But because what you have done so far was just potential at a point, but it's always this, right? It's a relative. It's always potential difference. So this final problems that I want to show you is every time you want to compare between one point to another point, all you care about is this, guys. You want to calculate. If you want to find the work done going from B to A, right? All you need to do is just take the charge, number 3, this is a charge that you want to drag, multiply by the delta V between B and A. That's it. That's all you care about. No? Multiply by the potential difference between 2 points. And as I emphasized throughout the course, delta means the final minus initial. So that means you have to take Q3 multiply by V at A minus V at B, and you are done. Isn't that cool? Okay, so that's what I say. This is potential difference. It will allow you to get the right away. A here is higher than V at B. The delta is automatically positive. When the delta is positive, means you're going uphill. Definitely, the energy must be positive too, because you have to supply the energy to the system, right? On the other hand, if you want to go backward, but if you want to take a back to the problem, it will be positive. It's going to be negative because now you're going down. Energy will be negative automatically because you gain something back from the system. Perfect, no problem. And but this diagonal line. Why don't you care about the diagonal path? It's independent. We don't care. That's the whole concept of potential. When they say they do this, I can go lift up like this is MGH. I can do this is MGH. I can do diagonal MGH. It doesn't matter. It's MGH. So you're gonna do diagonal. You're gonna do curve. You're gonna do circle. You can travel to multiverse, come back. It doesn't matter. All right. You get the same amount. Multiverse maybe not. All right. But I mean, because they might not have the same physics as ours. All right, guys. That is it. All right, for the whole business here, and we're done for this handout. Thank you. All right. Any questions? Yes. Oh, very good. If Q3 is negative, you put it there. Doesn't matter. Because by having the two types of charge, the negative charge will do everything opposite to the positive. So the positive charge will behave like our mass here, right? It will go from high to low on itself. But if you have a negative charge, it will go backward. It will automatically go from low to high. So that means if Q3 is negative, you put negative there. If Q3 is positive, you put positive there. Your interpretation of the final value will be exactly the same. Yeah. All right, very cool. All right, guys. So I'll see you guys on, all right, Wednesday, definitely. Okay. And Thursday, if you want, you can show up at 2 o'clock. So there will be Q&A for the section number 2. So you can join in as well. All right. And the exams will be 2 sessions, just like before. You can choose to do 4 to 6 or 6 to 8. All right. But for those of you that join the 4 to 6, have to stay until the end of the exam. Okay. All right, guys. Thank you. All right. Any questions now? ครับผมอะไรนะ Doppler equation อ๋อหมายถึงว่าในคำตอบในข้อสอบจริงมีกี่ข้อคง8 ข้อเหมือนเดิมอันนั้นเป็น collection เฉยๆเฉลยอะไรไม่เฉลยไงมา Q&A ไงไม่ทันทำไม่ทัน
ข้อ2 H เนี่ยข้อ2 H เนี่ยเยอะมาก2 H มันถามว่า converse speed of a string ใช่ไหมเราใช้สูตรนี้ได้เลยไหมสูตรนี้ได้เลยปะแล้วเราเปลี่ยน y เป็น x ได้เลยแต่ขัดบอกว่าเปลี่ยนได้เลยมันไม่ได้ไม่ใช่
พูดถามใหม่ดิถามช้าๆฟังไม่ทัน
ก็คือ
มัน flashy มากไม่รู้พูดถึงอะไรงงขอคำถามใหม่อีกที
transverse speed
transverse speed
สูตรนี้เราใช้สูตรนี้ได้เลยใช้
transverse speed
ใช้สูตรนี้ได้เลย
ถ้ารู้ y ก็ใช้ได้
แต่เราไม่รู้
ถ้าเราไม่รู้ก็ plug in back เข้าไปใน expression
ก็คือต้อง plug in แบบเข้ามาไอตัวนี้เพื่อหา y
ใช่ differentiate differentiate ข้อไหนข้อ
ที่แผนหนึ่งเราแต่ได้ส่งออกมาถามว่าด้านล่างจะไม่โดน
โอเคอันนี้ไม่ยากเราเดี๋ยวอาจารย์เขียนในนี้ให้21อันนี้มันเป็นข้อสอบเก่าเปล่านั่นน่ะเดี๋ยวอาจารย์สต็อปอันนี้ก่อนนะแป๊บนึงปึ๊บ